Hello and welcome. I want to make a quick video on the Heisenberg Uncertainty principle. Now, the Heisenberg Uncertainty principle is a very famous equation, a very famous principle, mainly through pop culture, but today we're going to talk to or learn about it in a manner of physical applications in physics and quantum mechanics. And so let's go over a little background real fast. So we know from de Broglie that the momentum of a particle is related to 2 pi h bar divided by its wavelength. So the momentum and the wavelength of a particle is directly related or inversely proportional to each other. We know that from de Broglie. Now, let's talk about what the actual equation for the Heisenberg uncertainty principle is. So the actual equation for it is the deviation in x times the deviation in p is greater than or equal to h bar over 2. Now what this means is there's an inherent variance in your x measurement and an inherent variance in your momentum measurement. So, as we stated in the last video on operators, since the wave function is really a probability distribution, there's some variance in what your values you measure could be. So let me give an example, just like a regular sine wave. Say our wave function is just this. This is psi. And this is x. So, this is our wave function right here. Now, as you recall, our probability for the wave function is actually the modulus squared of psi. And I will write that here. It actually looks like, well, first sine, so say psi equals sine of x, modulus squared is just going to be sine squared of x, because there is no complex part in sine of x, so it's just going to be sine squared, the wave function squared. And so what the wave function squared of sine looks like is something like this. Not really drawn to scale with this, kinda. It's not that great. But either way, this graph will get the point across. So this is our probability as a function of x. And as you can see, we have 2 peaks in probability right here and right here. And a dip in probability right here. So we have 2 areas, this part and this part, where it's more probable to find x than here at all. So, what that really means is if you take measure this repeatedly many times, you can find x here, you can find x here, you can find x here, you can find x here. But if you keep doing it, you'll mostly find them here and here, with a little bit coming down, but like never here, never here, never here. Not never, but close to never. So, this spread right here is what signifies sigma, the variance in x, how much this varies. Now, let's think of something else. Let's think of the wavelength of this sine. So, as we know, momentum is related to the wavelength. And we know the wavelength right here. The wavelength here is one wavelength, 1 meter or something. So, the variance in that is very little. We know we have more confidence in the momentum of the system than we do in the position, because the position could be either here or here. We don't know, but we know the wavelength. Well, the wavelength we know almost certainly. So the momentum we know almost certainly. That means we have to have more uncertainty in x. Let me give another example real fast. So, let's say we have another psi function, and this is going to be called a delta function. We'll learn more about this later, but it's basically 0 everywhere except for one spot. Imagine this is just one spot right here. So this right here means that we know for almost for a fact, well, here, let's do this. Psi squared still, if you just you square 0 a bunch, it's 0. If you square infinity, it's infinity. So we just still get another delta function. So our probability is exactly the same. That means we're pretty certain that we're going to find x right here. Like almost 100% certain if this is a real delta function, but we'll just pretend it's like very, very spiked right here. Maybe you could get a little bit out here, a little bit out here, but it's very certain right here. So that means sigma x is very low. We have almost no variance in our x variable. But what's the wavelength of this? This is a weird wave, isn't it? There is no wavelength. If it's a true delta function, there is no wavelength because there's no gap between here. For this, maybe there's like a tiny little wavelength right here, a little bit, a tiny little wave. But that means we have complete uncertainty in the momentum. So our uncertainty in the momentum goes up. We have no idea what the wavelength of this could be. And so this is just kind of a visual representation of how if you have high confidence in one, you have to have really low confidence in the other. And then vice versa here. We have high confidence in what the momentum is because we know the wavelength of this function. But the uncertainty in the position is higher because it could be here or here. We have 2 spikes in probability on this. And even the probability could come out here even too. So, and then there's a lot of math behind it to find why it's h bar over 2. Maybe I'll go over the math in another video, but I just wanted to show that this is more of an explanation of why this is true so much, not like a derivation of the Heisenberg uncertainty principle. I hope that helps clear up what the Heisenberg uncertainty principle really is. And just keep this in mind when solving a lot of equations or even problems, that this is always true for every realistic psi equation. Alright, thank you.